In the last couple of videos, I talked about using indicator variables to model differences between categories or levels in a qualitative predictor where we had two levels or categories in our qualitative predictor. And in this video, I'm going to run through an example where we've got three levels or three categories in a qualitative predictor. So when we have three levels, we need two indicator variables to code the information. So in general, if we have L levels or L categories, then we need L minus 1 indicator variables. So with two levels, we needed one indicator variable. Here we've got three levels and we need two indicator variables. If we had four levels, we would need three indicator variables, and so on. And so just as in the two-level example, for each of our indicator variables, we need to select a reference category. And so just as before, it doesn't actually really matter which level we pick for our reference level, because our final model results are going to be the same regardless, but we need some kind of rule of thumb to select one of the levels to be the reference level. So it's often going to be either the most common category or some meaningful baseline category. And in other instances, if neither of those cases hold, then we just have to choose one of the levels arbitrarily. So that's what I'll do here. I'm just going to pick one of the three levels. And this particular example, we've got revenue and cost data for three different states. And so I'm going to just pick one of the states to be my reference level. So I've got Oregon, California, Washington, so I'm just going to pick Oregon as my reference level. And as we went through in detail in a previous video, it doesn't really matter. Okay, as long as you know which level you have selected for your reference category, the final model results will be the same regardless. And we'll see that later on. So, once we've decided which is our reference level, then we create the indicator variables as follows. So I've got two indicator variables because I've got three levels. I've picked my reference level, which is Oregon, and the reference level has zeros for the two indicator variables. So 0 for D1 and 0 for D2. And then I go through each of the other levels, or each of the other categories in turn, and assign a 1 for the corresponding indicator variable and a 0 otherwise. Okay, so California is 1 for D1 and 0 for D2, and Washington is 0 for D1 and 1 for D2. So how is this going to help us model differences between the three states? So let's think about that in terms of a possible model. So here's one possible model where I've got cost as one predictor, D1 as another predictor, D2 as a third predictor, and then I've got interactions between D1 and cost and between D2 and cost. Okay, note that it doesn't make any sense for me to create an interaction between D1 and D2. Why is that? Well, if we go back here to our table, if I multiply D1 by D2, I would get 0 for Oregon, 0 for California, and 0 for Washington. So it would be 0 for every state in the data set, and so there's no information there. So a D1-D2 interaction wouldn't make any sense. So the only interactions that we include are between the indicator variables and the quantitative predictor cost. And I'm claiming that this would allow for different intercepts and slopes for each state. So what do I mean? Well, what I mean is, if we think about what this model is doing, it's allowing us to model the expected revenue for a particular cost for different states. So in other words, I could think about this in terms of a scatter plot where I have revenue on the vertical axis, cost on the horizontal axis, and I would have three separate lines, one for Oregon, one for California, one for Washington. And I'm claiming that those three lines would have different intercepts and different slopes based on this model. So how is that? So here's my model again, And what I'm going to do is I'm going to plug in d1 equals 0 and d2 equals 0 and simplify the resulting equation, and that will give me an equation for Oregon. So let's do that. So plug in 0 for d1 and 0 for d2, 0 for d1, 0 for d2, simplify. Okay, all these pieces of the equation with zeros in are obviously just going to go away, and I'll be left with b0 plus b1 times cost. So this is the regression equation for Oregon. What about for California? So California has d1 equal 1 and d2 equals 0. So now I'm going to plug in 1 here and 1 here and 0 here and 0 here. So 1 here, 0 here, 1 here, 0 here. So the bits with the zeros will go away, and I'll be left with b0 and b1 cost and b2 and b4 cost. So if I collect together the intercept pieces, it'll be b0 and b2, and the slope pieces will be b1 cost and b4 cost. So I could represent that like this: b0 plus b2 for the intercept, and b1 plus b4 for the slope. So this is the equation for California. And then I would do the same for Washington. Washington has d1 equals 0 and d2 equal 1. So now I'm going to plug in 0 here, 1 here, 0 here, and 1 here, and I'm going to get, oops, I didn't mean to do that yet. Let's undo that. And how far down do I need to go? Nope. Where's my equation? It's somewhere here. Here they are. Okay. So this piece of the equation will go away with the zeros. These pieces, I'm going to have b0 plus b3 for my new intercept, and b1 and b5 for my new slope. So this is the equation for Washington. Okay, so if we look a little more closely at what's going on, if I compare the intercepts between California and Oregon, okay, so here's the intercept for California is b0 plus b2, the intercept for Oregon is b0. b2 represents the difference in the intercept between California and Oregon. And let's look at the slopes now between California and Oregon. b4 is the difference in the slope between California and Oregon. Okay, so we talked about this in the previous videos where we were looking at two levels. Now it's the same kind of phenomenon, only there's a little bit more going on, so we have to be very pay attention to what's going on. But if we look at our original equation, this regression parameter that multiplies d1 represents the difference in intercepts between the level indicated by this indicator variable, which is California, and the reference level, which is Oregon. And if we look at b4, that's multiplying d1 times cost, that represents the difference in slope between California and Oregon. So this is how regression parameters that multiply indicator variables, or interactions between indicator variables and quantitative predictors, represent differences either in intercepts or slopes between that level or that category and the reference level or the reference category. So you should be able to see a similar phenomenon going on with b3 and b5. b3 is the difference in intercept between Washington and the reference level, Oregon. And b5 is the difference in slope between, with respect to cost, between Washington and Oregon. Okay, so that's the sense in which this model allows for different intercepts and slopes for each state. Okay, so let's look at all this. So let's go back to R and fit that model. So here's a summary of the model. So all these numbers are the estimates of all these regression parameters. Okay, so overall intercept, well, actually this represents the intercept for Oregon. If we go back here, B0 is the intercept for Oregon. Here's the slope for Oregon. Here's the estimated difference in intercept between California and Oregon. Here's the estimated difference in intercept between Washington and Oregon. Here's the estimated difference in slope between California and Oregon, and here's the estimated difference in slope between Washington and Oregon. But if we look at the significance of each of those regression parameters, two of them have very high p-values, and perhaps we'd be better off excluding these two terms from our model. Perhaps we'll end up with a better model, one that's a little tighter, doesn't have any extraneous information in, and perhaps will predict better, generalize more to the population beyond our sample, and give us more accurate predictions. So we talked about comparing models before, and so what we would do here is let's see if we can remove D2 and D1 cost from the model by doing a nested model F-test. So I'll fit a second model without those predictors. So I've dropped D2 and D1 cost, and I've obtained this model. And let's have a look at the nested model F-test results. So here's the F statistic, and here's the p-value. The p-value is bigger than a significance level of 0.05, so that means that we fail to reject the null hypothesis. The null hypothesis says that in this model, what are we testing? We're testing that D2 and D1 cost. So we're testing B3 and B5 both equal to 0 in the null hypothesis. So we can't reject that null hypothesis. So if B3 was 0 and B5 was 0, if they were both 0, then I can drop D2 from the model and D2 cost from the model as long as I retain everything else. Okay, so that's this p-value here that I'm looking at. What else suggests that perhaps my simpler model is preferable to my more complicated model? Well, if I look at the regression standard error, I've got 0.1379 in the model with everything in it, and that comes down to 0.1204 for this simpler model, which removes those two redundant terms. So I'm getting a better model in terms of prediction accuracy, and we can also look at adjusted R squared, 0.9845 for the model with everything in it, and that increases to 0.9882 for this model, this simpler model. So from all three perspectives, having these two terms in the model seems to be causing overfitting. So that brings us to this simpler model. So that was this output here, and I can use this to obtain an equation, a fitted prediction equation for revenue based on cost and which state. So here's B0 hat, here's B1 hat, and so on. So here's my full equation. Okay, and actually let's go to here again. Okay, so here's my full equation. So I'm just getting these numbers from this coefficients table here. And again, I could simplify this equation by plugging in D1 and D2 to get equations for Oregon and California and Washington separately. So let's just quickly run through what that would look like. So plugging in D1 equals 0 and D2 equals 0, that's going to give me the equation for Oregon. So intercept and slope for Oregon. If I plug in 1 for D1 and 0 for D2, that's going to give me the equation for California. Okay, so same slope, but a different intercept because I've got 25.683 here and minus 0.829 here, so that comes to 24.854. And then for Washington, D1 equals 0 and D2 equals 1. And so now the intercepts are the same, but the slopes are different because I've got 5.433 plus 2.004, 7.437. Okay, so what does this look like in a graph? So let's have a quick look at a graph. Okay, so here's let's zoom in. So here's a graph of what's going on. I've got revenue on this axis, on the vertical axis, cost on the horizontal axis. My points are marked according to the state, and then these are the regression lines. And Oregon, this was my reference level, and then California has a line that's got the same slope. But if I was to trace this line back to when annual costs are 0, they would cross the axis at different points, so they've got different intercepts. Whereas Washington has a different slope to the Oregon line, and if I trace back to where cost is 0, those would both have the same intercept. Okay, so this represents this fitted model here. So one thing I've done here is I've ended up with a model that doesn't actually retain hierarchy. We talked about hierarchy before, where if, for example, I have an interaction between D2 and cost, I should really have D2 and cost in the model as well. And I do have cost, but I've dropped D2 from my model. So some people don't like to do that, to have models that don't respect hierarchy like this. And so some people would just stop here and say, okay, this model is fine and it respects hierarchy. It doesn't matter that I've got a high p-value here because I need to keep the interaction in the model. So they might consider getting rid of this term, D1 cost, but they would keep D2 in the model. I don't think it actually makes that much difference in this case. After all, whether you keep D2 in the model or not doesn't really matter because its regression parameter estimate is not very big. Okay, so the equations you end up with at the end are really going to be very similar whether you keep D2 in the model or you get rid of D2. I like to get rid of it because, as I say, the model with D2 seems to be overfitting, and so as long as this model makes sense, then I think it's okay to not retain hierarchy in this case. So in general, how do we use qualitative predictors in practice? So we've looked at an example with qualitative predictors with 2 levels and with 3 levels. You can employ the same ideas with qualitative predictors with more than 3 levels. So for example, let's suppose we had an application where we had 2 qualitative predictors, and one of them had 2 levels and the other one had 4 levels. So if we believe, or we have evidence, that the association between a quantitative predictor X and the response variable Y could differ for those 2 levels of the first qualitative predictor, then we would need an indicator variable to model that difference between the 2 levels, and we might also want to include a D1X interaction as well. If we believe that the association between X and Y could also differ for the 4 levels of the second qualitative predictor, then we're going to need 3 more indicator variables. So let's say D2, D3, and D4, and include those in the model together with their interactions. So you can see that you can model lots of different relationships between a response variable and quantitative predictors, and model differences between levels of qualitative predictors as well by using indicator variables in this way. Again, as we've talked about before with model building in general, you have to not make things too complicated, because you can end up either overfitting the data or end up with overcomplicated models that are very hard to interpret. So this should be done judiciously, and I've got within reason here. Let's say you have a qualitative predictor with 100 levels. It's unrealistic to think that you could model that by using 99 indicator variables. Okay, for sure you're going to be overfitting the data at that point. So judicious use of indicator variables, just as with all regression modeling, is you can't go crazy with this stuff. You've got to keep things in perspective and keep things manageable. So that brings us to the end of talking about qualitative or categorical predictors, and in the next series of videos we'll go on to talk about other aspects of model building, in particular looking at influential points, thinking about various regression pitfalls that can occur during the process of a multiple linear regression analysis, and then we'll also look at in a little more detail at the predictor effect plots that I introduced in previous videos.